Today we will start the module 4 which is actually the constitutive relation 2 itself. So, constitutive relation itself. So, in case of this module 4 we will be basically discussing the isotropic elasticity and the constitutive behavior of composites. So, in the last class we have derived the monoclinic and triclinic material. What we have found is essentially from 81 elastic constants to 21 independent elastic constant for the triclinic material. Now, for the monoclinic, where one plane of reflection symmetry exists, there we found it is 13 constant, 13 independent constant, and we know how to derive those constitutive equation from our last lecture. Now, then what we did in where we have 3 planes of mutually orthogonal, mutually perpendicular planes, that is orthogonal planes of symmetry, reflection symmetry. There we have derived the constitutive equation for the orthotropic material. So, now here what we are doing essentially is we are using the invariance of the strain energy function. So, with the invariance of the strain energy function under reflection or rotation, the strain energy function does not change. So, we use this thing to derive the specific constitutive metrics for the different class of material. Now, anisotropic material. Now, this is from the last slide. So, the approach in the strain energy invariance is as follows. Suppose there is a plane of symmetry. If I transform the coordinates by mirror image and about a plane of symmetry, we should have a following relation. That is as the strain transforms, constitutive relation will also transform. So, there will be two different constitutive relation in two different coordinate axes, and this will be equal because rotation about a plane of symmetry, and also considering the fact the strain energy is a scalar. So, it should be invariant under coordinate transformation. So, by this we eliminated some constants from 21 independent constants to for the monoclinic material 13 independent constant, and for the orthotropic material 9 independent constant. So, we will further reduce this number of independent constants from 9 to 5 for transverse isotropic material, and finally, for the isotropic material it is 2. So, today we will see how this can be done in the framework that we have studied. Now, for a orthotropic material, as I have told just now, is the 3 plane of symmetry or reflection about 3 orthogonal planes. So, it is essentially x1 x2 plane, x2 x3 plane, and x1 x3 plane. So, now there are 3 rotation metrics we can derive. So, what we did in the last lecture is that we assumed the 2 plane of symmetry, and then we derived it. So, it can be proved that if there is a 2 plane of reflection symmetry exists, then third plane is also having the reflection symmetry. So, now this is the constitutive relation that we have derived in the last class. So, now here the basic purpose is this giving this slide is basically we will use this constitutive matrix in the subsequent development. Now, the strain energy density it is can also be written which we know from our previous module, that strain energy density can be represented as half of u strain vector, it is a vector transpose C epsilon. This form we have seen in the void notation, and then also in the general this thing that tensorial notation strain energy can also be represented, and this is the void notation stress strain relation. So, now here we have used the strain tensorial component of the strain, that is epsilon 1 1 epsilon 1 2 and etc. So, this is the strain energy function for the orthotropic material. Now, from here let us assume that material is orthotropic, that is there is a reflection symmetry about 3 or the reflection about 3 orthogonal planes, and then we deduce the basically the transverse isotropic material constants. So, first of all the word isotropic means what? The isotropy, so first we will discuss what is isotropic or isotropy essentially. So, isotropy means, from our strength of material background, so you all know that is uniformity in all orientation and identical values in all direction or orientation, whatever it is. So, we know that, because isotropic case we have learned first, which have 2 material constant in terms of Young's modulus or Young's modulus and Poisson's ratio, or in terms of shear modulus and Young's modulus, whatever, or bulk modulus, whatever you assume. So, now we will also know that if there is a orthotropic plane, a isotropic plane, then there is a x1 and x2, if that means x1 x2 in this direction, E1 and E2 are same. So, we know this from our basic relation, basic knowledge of isotropy. So, nu 1 2 is essentially nu 2 1 is essentially nu, and shear modulus is not independent, it is E by 2 into 1 plus nu. So, this we know from our basic strength of material knowledge. So, now a plane of isotropy, what is a plane of isotropy essentially? So, we understand from the definition what is plane of isotropy, but let us give a formal definition. So, a plane of isotropy at a point, a plane of isotropy at a point of an elastic material body is defined as a plane for which there exists a infinite number of perpendicular planes of elastic symmetry. So, that means if this I consider x1 x2 as a plane of symmetry or plane of isotropy, then there is an infinite number of elastic symmetry exists along the x3 axis or perpendicular axis. So, this is what plane of isotropy means. So, now elastic symmetry at a point of an elastic material body is defined as a plane for which material exhibits reflective symmetry. Reflective symmetry means we know that what is reflective symmetry. If you remember for our monoclinic material, where we just x1, x2 and x3 what we did sorry x3 x2 and x3. So, what we did basically, we essentially transferred this to this x2 minus, so x2 dash. So, this is x1 and this is x3 dash. So, basically x1 x2 x1 x3 plane is having the reflection symmetry. So, now this is this is known as the elastic symmetry. So, this is we know from our previous lecture. Now, what we know is essentially we know the isotropic means, what does it mean for isotropy, and what does it mean for an isotropic plane. Now, also we know that we have 3 reflection symmetry for or the reflection about a plane, mutually orthogonal or mutually perpendicular plane for an orthotropic material. So, with this knowledge we will proceed to derive the transverse isotropic material. Now, what is transverse isotropic material? The transverse, the word transverse means here actually here if you see this figure tells you what is the transverse isotropic material. This is a fiber along this direction, and these fibers is having a plane of symmetry about this hash line. So, about this hash domain, this is a plane of symmetry. So, if you move along this, if you move this hash portion, you will get the same properties. So, that is the idea. So, now for an isotropic, transversely isotropic material, we are starting with the orthotropic material. So, orthotropic material, we know that three reflection symmetry or the mutually orthogonal planes of having reflection symmetry. So, this condition is coming from the orthotropic condition, and for which we know the constitutive matrix. So, and which is having 9 independent constants. Now, in addition to that, if I assume that there is an axial symmetry with respect to an axis, that means if I about this axis there is an axial symmetry, and normal plane to that axis is known as the isotropic plane. So, that is clear from our definition, previous definition, that about this axis there is a axial symmetry, and normal to this plane is an isotropic plane. Now, with this assumption, what should be the constitutive relation? So, first let us summarize what are the assumptions we are making here. First we are making these 3 mutually orthogonal planes of reflection symmetry, which is essentially the orthotropic material, and the orthotropic material we know the constitutive equation. Second is that axial symmetry with respect to an axis. So, along this axis, if say this is an x1 axis, so about x1 axis there is an axial symmetry. So, that means that x2 x3 plane is essentially the x2 x3 plane is essentially the isotropic plane. So, now with these two assumption, if I rotate this body about x1 with an alpha, if I rotate this body with an alpha, then I know what is the constitutive, what is the coordinate transformation. So, the new coordinate system is x1, x2 prime, or x2 dash and x3 dash. So, if I rotate this material about x1 with an alpha, so x1 will not change. So, x1 prime will be x1, and x2 prime will be x2 cos alpha, x3 sin alpha, and x3 prime will be minus x2 sin alpha, x3 cos alpha, which is coming from this rotation matrix Q. So, this we know from our basic knowledge. So, with this knowledge, let us see what is the strain component we have. So, now with this thing, let us convert the strains. So, strains, converting the strains, we know the strain formulas. Converting the strain formula, this is in a essentially tensorial notation, and this is the indicial notation. So, if you transform this, so epsilon dash 1 is epsilon 1 and epsilon 2 is epsilon 2 cos 2 alpha, and these cos and sin alpha are coming from the Q's. So, which was in the earlier in case of a monoclinic and orthotropic material, it was only 1. So, because there was a reflection symmetry. So, now here it is not a specific rotation. So, any rotation is possible. So, alpha is essentially cos alpha and sin alpha. So, now epsilon 2 prime, epsilon 3 prime, epsilon 2 3 prime, and all the components I have multiplied with this. Essentially Q is a matrix which is this, and epsilon we know epsilon is a second order tensor, strain tensor, which is having epsilon 1 1 and epsilon 2 2 and so on. So multiplying this I get this transformed strain components which is in the prime coordinate system, and the prime coordinate system is x1, x2 prime, x3 prime. Now if you look carefully these two what is the relation of the strain components in these two coordinate system. So if you look carefully you will see that epsilon 2 prime and epsilon 3 3 prime will be summation of these two strain component will be equals to non-prime component. So this is an invariant within this about an axis rotation. So if you it can be derived very easily if you sum up epsilon prime 2 2 and epsilon prime 3 3, then these two quantities essentially give me the sin squared alpha plus cos squared alpha is 1. So it is giving epsilon 2 2, and then epsilon 2 3 component cancels, and then epsilon 3 3 is again sin square alpha plus cos square alpha. Similarly, epsilon 2 2 prime and epsilon 3 3 prime minus epsilon 2 3 prime square equals to non-prime coordinate system. So this is also you will see that if you exercise this, so you will see this is a invariant quantity. Now similarly epsilon 1 2 prime square and epsilon 1 3 prime square is epsilon 1 2 square and epsilon 1 3 square. So this is also a invariant. So this can be very easily seen. So now these quantities essentially doesn't change. So what it means is essentially these quantities doesn't change if I rotate about an axis x1 to a specific rotation alpha, any rotation. Now another quantity which is essentially doesn't change is the determinant of the strain tensor. Now you know that determinant of Q is here plus 1. So this can be easily checked by this formula. So determinant of epsilon prime is essentially equals to determinant of Q epsilon and Q transpose. So the product of two matrices we know the determinant is multiplicative. So determinant of Q epsilon Q transpose is determinant Q, determinant epsilon, determinant Q transpose, and Q transpose determinant is also plus 1. So it gives the determinant of epsilon prime is equals to determinant of epsilon. So this is also invariant quantity. So basic idea from this is that this doesn't change these quantities. So if I give an alpha rotation, so this doesn't change these quantities doesn't change even if I rotate the axis. So this is the basic idea. So now if these quantities doesn't change, then my strain energy also should not change by rotation of this. So naturally my strain energy will be function of these quantities. So this is very obvious because strain energy is a scalar and it will be invariant. So obviously this strain energy function will be based on this. So we will use these or we will exploit this fact to derive the constitutive equation for the transverse isotropic material. So let us see. So hence strain energy function to be invariant of the form must be of this form. So now you see it will be epsilon 1 1. So clearly epsilon 1 1 also doesn't change during this thing. So it will be function of epsilon 1 1, epsilon 2 2 plus epsilon 3 3, epsilon 2 2 epsilon 3 3 minus epsilon 2 3 square, and epsilon 1 2 square epsilon 1 3 square. So now following the orthotropic material, so we will start with the orthotropic material because in case of a transverse isotropic material the orthotropic assumption is valid. So, in addition to the orthotropic assumption, there is a axial symmetry about an axis. So, so the strain energy function is this. Now, if you look carefully in this strain energy function, so this I have manipulated a little bit to make the specific quantity in the specific braces. So, this quantity, if you look carefully, so it has to be a function of epsilon 22 plus epsilon 33. So, naturally C11, C12 and C13 has to be equal. Unless this becomes equal, so this cannot be epsilon 22 plus epsilon 33. So, first assumption is first thing is that C12 equals to C13. So, this is one condition. So, first thing we have understood is that C12 is C13. So, if you remember the constitutive equation of the orthotropic material, that orthotropic, in case of orthotropic material, that C12 and C13 are not same. So, it is different. So, if you remember that constitutive matrix for an orthotropic material, C11, C12, C13, C22, C23 and C33, and then C44, C55, C55 and C66. So, these are the zeros and this is symmetric. So, now see, for an orthotropic material C12 and C13 was different. Now, if I assume this transverse isotropic condition, then I have to have this C12 equals to C13. Now, similarly, if the strain energy has to be function of this quantity epsilon 12 and epsilon 13 square, then C55 and C6 has to be equal. So, this condition again gives me that C55 equals to C66. So, these two, so we have reduced it. Now, from orthotropic we have a 9 constant. So, we have reduced it here 1. So, and we have reduced it here 1. So, we are now in the 7 constants. So, now let us see how we can reduce it further. So, let us go to next slide. So, now this was my condition. So, now here what I have done is I have incorporated these two previous conditions C12 equals to C13 and C55 equals to C66. So, it is in terms of C66 and C12. So, there is no C13 and C55. Now, if I, in addition to, so this was the last term in the braces. So, we have finished with these terms. So, these terms are as per the invariant quantities. So, now, but this term we have to make as per the invariant quantities. So, now, if we assume C22 and C33 again, then what will happen? It will be a function of epsilon 22 and epsilon 33 square. So, here, so if I assume this C22 equals to C33, then it will be function of epsilon 22 square and epsilon 33 square. So, which I can again, if I manipulate this with this assumption, so I can write this last quantity in terms of this, right. So, which is essentially plus minus of some quantity, which you can try simply, you can pen and paper, you can try it. So, once we are done with this, then we can see that it is a function of epsilon 22 and epsilon 33, which is as per our assumption, that is invariant quantities epsilon 22 and epsilon 33, and then again this quantity is left. So, now you see it comes in the form of this, but we need to change the material constant. So, now if this has to be a form of this, then 2 C22 this quantity C22 minus C23 has to be 2 C44. So, now this gives me another condition, which is essentially C44 equals to C22 minus C33. Now, here, now finally, what we got? We got C12 equals to C13, C55 equals to C66, C22 equals to C33, and then again this condition. Now, finally, with these things, if I plot, if I write the strain energy function, it looks like this. So, this is the epsilon 1 squared, epsilon 2 epsilon 3 and epsilon 1 epsilon 2 epsilon 2 plus epsilon 3 and this last invariant quantity. Now, see, that means if I write the strain energy in the transform coordinate system u prime, so u prime will be u. Why? Because these quantities does not change, as we know that epsilon epsilon 2 plus epsilon 3 is essentially epsilon 2 prime plus epsilon 3 prime. So, we know this. So, similarly for these quantities. So, essentially with this rotation plus orthotropic assumption, orthotropic symmetry, strain energy will not change. So, that means this is my these constants, these C11, C12, C66, C22 and these are essentially my material constants. So, if I now write it in a formal matrix form, how it looks, let us see. So, it looks like this. So, if you see carefully, these C11 C11 is essentially this C12, C22, C23 and C66 is my independent constant. So, essentially isotropic material, a transverse isotropic material is 5 independent constant. So, this is how we represent any transverse isotropic linear, obviously linear elastic transverse isotropic material which follows the Hooke's law. So, now if you have derived for transverse isotropy, then we can simply derive for isotropy very easily. So, it is in case of a transverse isotropy, we have seen that it is for the one plane of isotropy. Now, if I assume instead of x1 symmetry about the x1, so in case of a transverse isotropy, we have seen that we have assumed that x1 is my the about an axis for which that means that x2 x3 and x2 plane is my isotropic plane. So, now similarly in addition to that, if I assume about x2, that is x3 x1 is also an isotropic plane and x3 about an x3, that means x1 x2 is also an isotropic plane. So, if I assume 3 mutually perpendicular isotropic plane, then it can be proved that isotropic material constant is having the only independent number is 2. So, because if you just do this, then it is very simple exercise that all these quantities will be this and these quantities will change it to 2. So, so finally isotropic material will have C11 and C12. Now, if I assume this C11 and C12 by 2 is mu and mu is will define what is mu and then C12 is lambda, then C11 is lambda plus 2 mu and this lambda and mu are called Lamé coefficient. So, mu is essentially some of you must have known this earlier, that is mu is essentially the shear modulus which is E by 2 into 1 plus mu, 1 plus nu, the Poisson's ratio. So, essentially we can write that isotropic constitutive 3D isotropic constitutive relation, and in the tensorial form also we can write it in this form, that sigma ij, lambda ij, delta ij, epsilon kk and 2 mu epsilon ij. So, lambda is essentially known as the first Lamé constant. So, lambda is also, some of you probably know, which is E nu 1 plus nu into 1 minus 2 nu. So, and then mu is essentially the shear modulus G, essentially E by 2 into 1 plus nu. So, these two constants we know. So, now what we have in a closing remark, what we have done here? We have started with general isotropic material. That means the isotropic parameters, which is essentially general anisotropic material, for which the constitutive matrix is a we know that C colon epsilon, or the inner product with epsilon, where C is essentially fourth order tensor IJKL. So, now to summarize it, C IJKL will have 3 to the power 4, that is 81 constants. Now, from these constants what we have done, we have assumed measured symmetry and minor symmetry with these two, and the existence of the strain energy function, where we have, if you remember, where we have explored the partials, that is del square u by del epsilon ij, del epsilon KL is essentially equals to del squared u by del epsilon KL and del epsilon ij. So, with these three conditions, from 81 constants to, we reduced it 21 constants, 21 independent constants. So, now from these 21 constant is for a general anisotropy, which is known as allotropic material or the triclinic material. So, from this triclinic material, again we assume some symmetry condition. First, what we have done? We have done for a symmetry, reflection symmetry about a plane. So, so first is known as the reflection symmetry of a plane. So, which is known as the monoclinic material. So, which is having the 13 independent constant. So, from 21 to 21 is for triclinic, then we derived it from 13 to triclinic material, and then instead of a one symmetric plane, if we assume 3 mutually perpendicular symmetric plane, then we got the constitutive matrix for an orthotropic material, which is having the 9 independent constant. Then if we assume from orthotropic material, with that means there is a 3 plane of symmetry or the 3 symmetry plane about 3 mutually perpendicular axis, and then from there additionally we assume that there is a axial symmetry and there is a plane of isotropy normal to that axis. So, if we assume that, then we got the transverse isotropic material, for which there is a 5 independent constant, and this is known as the transverse isotropic material. Then from the transverse isotropic material, again if we assume that there is a axial symmetry about all 3 perpendicular planes, and there is a reflection symmetry too. So, then from there we achieve the isotropic material, where the material constant is 2. So, finally, if you look carefully, that from 81 to 21, so 81 is not independent constant, 21 is independent constant. So, the process is 81 to 21, 21 to 13 and 9 and 5 and then 2. So, essentially the triclinic material, monoclinic material, orthotropic material, and then transverse isotropic material, and then finally the isotropic material. So, this was the most general way of and also there are some other material, for instance cubic material, which is having 3 independent constant. So, these can be also done very easily. So, I left this thing on you. So, here today we will stop here. So, we will follow in the next class. Thank you.